We're going to classify these mass movements based on the nature of the material, the speed at which the material moves, and the nature of that movement. It can range from imperceptibly slow movement to hundreds of kilometers an hour movement. We're going to break down mass movement of rock into three basic categories: rock falls, rock slides, and rock avalanches. Our first category of mass movement is pretty self-explanatory: rock falls. Our example here is the Palisades sill. If you were standing right about here, you could easily see Manhattan. You could see the Empire State Building, the Chrysler Building, the new Liberty Building. So you're not far from New York City at all. This is columnar basalt from a Triassic basalt flow. Now, where these big columns fall off, they're going to fall off as hexagonal columns. And you can see that maybe a little better highlighted here in the artist rendition than the photograph here. Regardless, this is a resistant rock ledge. There's some sandstone below and above. The sandstone above is all weathered away. Sandstone below is hidden from you in this image. What's happening is water is seeping into these fractures between the columns and expanding, contracting, expanding, contracting over the years. And eventually it's going to peel those columns apart and they collapse. A little more spectacularly is this video from Spain, in which some rock climbers are testing the stability of a rock, and it's not very stable. Now here we have a rock slide. In this case, frost wedging has loosened jointed bedrock layers, and that's most likely the case here. What isn't really quite accurate here in this image is this displays or depicts a shale layer here. The shale is going to be largely impermeable to water. So any water that falls on this porous material is going to soak in to the point that it reaches this shale. And it's going to lubricate the surface. So a better example here would be the Grovant slide. This is from a little bit north of Jackson Hole, Wyoming, near Moose, Wyoming, or the Tetons, you may know. And what this is a spectacular slide that I believe was 1925. It moved from this point up slope here, about 300 feet up the adjacent valley wall. Or adjacent valley slope. So material moved as much as 3 kilometers from here down slope and then through the valley and then up slope on the other side. And that's because it was cushioned by air. So it's sort of a combination of a bunch of different disasters here, in that we have, in this case in Wyoming, the Amsden Shale, which is a Mississippian age shale, overlain by the Ten Sleep sandstone, which is a fairly porous Pennsylvanian age sandstone that has a bit of Permian fossils right at the very top. So in the case of Wyoming, the Ten Sleep soaks up any rainwater. It increases the mass of this overlying material, this overburden, and the fractures within this rock, if given the chance, are going to break loose and allow this material to slide down slope. There was apparently a series of small tremors just prior to this landslide, and that probably served to break the material loose. Once it was loose, it slid rapidly down slope and lifted up into the air. So air provided a cushion beneath it, like the air under a air hockey game puck, and that allowed the material to fly down the valley, cross the stream, and then blast up the other side. Ultimately, it formed a huge dam here that produced Lower Slide Lake. In 1927, part of this dam gave way, and it flooded the town of Kelly just a few miles away, wiping out the town completely and killing 6 people. So pretty spectacular. You can see it from the air easily if you're flying over the western U.S. and you're near Jackson Hole or the Tetons. The pilot will say the Tetons are on your right. If you look just to your left, you'll see the Grovant slide here. So there was actually a cowboy on his horse right around here at the time of the slide, and he heard the crack and saw this material flying down the slope, and coming up the slope right to him, and it stopped right below, essentially below the horse's feet. And these were boulders, not just dust. So boulders came flying right up to him. So lucky guy and that he got to see it, and even luckier that it didn't kill him. And here's a closer view. You can see the 10 Sleep sandstones, this whitish color material. Can't see much of the Amsden Shale, maybe a little bit down here. All this debris that's been forested is from this landslide. So this is an enormous amount of material here that has moved down slope. Again, most of it is Pennsylvania aged sandstone with some soil and, of course, lots of trees on top. Rock avalanches depicted here. This is the West Salt Creek Avalanche in Colorado. It's about an hour east of Grand Junction, which is the southwestern corner of Colorado. In this case, an earthquake loosened a large mass of rock, and much like the Grovant slide, it was lofted into the air as it moved downhill. And as it moved downhill or down slope, on this air, that allowed it to travel much further than if it was merely falling and saltating down the slope. So it's been injected with air, and it travels, as you can see, quite a distance. These are some houses and barns for scale. Largest avalanche in Colorado history. Unconsolidated mass movements are going to range from barely perceptible, in fact, you'd only know that they happened if you had some basic background, to something that's totally spectacular. Starting with creep, this would be something you wouldn't notice unless you were tuned in geologically and geomorphologically to the world. So here we have the damage done to structures by creep. So we have bedding oriented like this, where the rocks meet the surface. That rock is converted into soil, and it's the soil that's slowly moving down slope. As it slowly moves down slope, the soil at the top moves a little bit faster than the soil a meter down, which moves faster than the soil a meter below that, etc. The net result is vertical structures appear to be bent. Trees will have their base turned, and the trees respond by continuing to grow vertically. Net result is the trunk of the tree is going to be curved. Fences are going to be bent and collapse eventually. Telephone poles lean. So it's not laziness or inefficiency or unskilled post hole work here. This is creep disrupting a fence. Something a bit more spectacular. Here we have rain soaking fine-grained permeable soils. This fine-grained permeable soil is going to be lubricated. The water is going to push the grains apart and make kind of a slurry. This slurry is going to be sitting on a steep slope in this case. And if you ever poured a Frosty or a iced coffee out on a slope, it will move downhill. Same kind of thing is happening here. Instead of chunks of ice in your coffee, it is chunks of rock. So because this is, again, lubricated with water permeable soil lying above water impermeable rocks, it's going to slide at a speed that is going to range from slow to moderate. Fast enough that you'd have to run or speed up your car. Debris flows are much faster. In this case, rain has soaked shale-derived muds and rubble that's overlying, again, less porous bedrock. In this case, the trees have been removed, although it looks like there were never really any trees here, so probably a bad image. Well, let's say there were trees here. We cut them down. The overburden is exposed. Underneath that, we have impermeable shale, and below that, jointed bedrock. And what's going to happen as the rain soaks this material, it destabilizes it, and again, it's going to flow downhill, in this case, fairly rapidly. So anything that sits in its way, vegetation or surface material, is likely to be scraped clean. Mud flows. In this case, the mud flow, it looks pretty clearly to be derived from a clear-cut area rather than a volcano, but the look would be similar. In the volcanic example here, we have a volcanic eruption like the Jökullaups in Iceland. It's going to melt snow and ice. It's going to soak unconsolidated volcanic ash, pyroclastic debris that is lying on top of impermeable lavas. The result is we have a mud that's going to be lubricated by large amounts of water, and this large amount of water on a steep slope is going to move down slope very rapidly. So this could be a lahar. And here we have a debris avalanche, something very quick moving, something very deadly. We have unconsolidated ash and rock, again, on top of a volcano. This volcano erupts, melting this glacial ice at the top, providing more water. The steep slope, combined with all this unconsolidated ash and water, results in a very unstable slope. In this case, the material flashed down the mountain and completely buried these two towns, killing an enormous number of people. And you can see the before and after images here. Essentially no trace of the town's remains, except maybe some houses over here. And here's something that's not quite dramatic, but it would be very upsetting if it was your property. This is Slump. If you want to see an example of this, just go to the University Bridge, facing downtown, and look to your left. The river bank is slumping, and it's become a geotechnical problem, as we say in the business. In this case, a mass of unconsolidated material is going to slide down as a unit, kind of like sticking a shovel in here, or shovel, scooping out these units of unconsolidated material that's going to slide down. But it's not going to slide down very far. It's far enough that it would destroy a road or a house or a river walk in the case of Saskatoon, but it's generally not going to be life-threatening. And then a debris slide. In this case, rock, soil, and surface features, such as trees, are going to move as units downhill along a plane of weakness. So little islands of trees, houses. We looked at a slide video earlier in the course in Norway, which basically was a village sliding towards the sea in Norway. Units of material going to move down slope and then accumulate at the base. Now, geomorphology is the shape of the landscape and the study of how those shapes develop. This includes topography, configuration of the Earth's surface, elevation, vertical distance above or below some standard, usually sea level, and relief, the difference between highest and lowest elevations. Topographic map shows the configuration of the Earth's surface using contours. These contours are lines that connect points of equal elevation. So here we have the topography of a mountain peak and river valley. The closer these lines are together, the steeper the slope. Further they are apart, the shallower the slope. So we can see here a pretty considerable difference between one side and the other. Very gentle slope on this side. You see the contours are far apart. Contours are very close together on this side. So this would look like a cliff face compared to a forested slope here. And the example down here is Flaming Gorge, Wyoming. So we have the river right here in the middle of the diagram. And again, widely spaced contours here, very widely spaced contours here, indicating it's relatively flat. Hey, it looks relatively flat here. Relatively steep over here because we're looking at this cliff face. We can convert this from a series of lines to color. And this is what you're more likely to see if you're using a GPS today as opposed to 10 years ago or 20 years ago when they were really just coming into development. We'll take a look at Turkey, or Anatolia as it used to be known. Here we see relatively high elevation indicated by this transition from yellows to browns, with dark greens being low elevation. And the rapid change in color in this map, as well as this map, is going to show us the change in relief, the steepness of the topography. Examples of landforms include rugged mountain slopes, river floodplains, and desert dunes. Flat-top landforms include plateaus, mesas, and tablelands. Most mountains are going to be found in ranges. There are isolated mountains in the world, Mount Kilimanjaro being an example. Most mountains, however, the vast majority are found in ranges. Some of these ranges are going to be structurally controlled, as we see here. These are the Zagros Mountains of Iran. Some of you may wonder, anything ever happened in the Zagros Mountains? Something very important in human history happened there. It's believed this is one of the locations where animals were first domesticated. There were sheep living in the Zagros Mountains in caves, and people noticed that behavior. Sheep like to live in caves. They live in herds. Hey, we can adapt that to our use. We can train them to live in a pen instead of a cave. We'll protect them so they don't need to hide in the cave. And because they follow or imprint upon one individual, the shepherd replaces the lead ram, the head male. So that happened here in the Zagros Mountains. For this class, this ridge and valley topography is generated from the erosion of folded sedimentary rocks. So here we have tributary streams on anticline. This is going to cut down through the anticline here, forming a valley. It's also going to cut down, this tributary stream is going to cut down in this orientation. The net result is we have valleys forming over the anticlines and ridges capped by resistance strata that are left over the synclines. Famous example of this are the flat irons in Boulder, Colorado. You can Google that. Boulder, Colorado, flat irons. And you'll see some resistant beds that are sticking up. So what does this look like on a geologic map? Looks like this. This is eastern Pennsylvania. The Susquehanna River has been around for a long time. It's been around longer than these mountains, which is why it cuts right through these mountains. There's another river further to the south off of this map known as the French Broad River. It's the oldest river in North America, believed to be about 285 million years old. That's a really old river. It's cutting through this rock, which has already been eroded substantially, leaving this valley and ridge topography. Taking a look back at the interaction between tectonics, climate system, and landscape development, we pretty much sum it all up here. We'll start out with the external heat engine, solar energy. That's going to evaporate seawater. That water moves in the vapor phase over land where it is uplifted and cools, forming precipitation. That precipitation weathers this uplifted rock physically and chemically, changing its physical characteristics, its appearance. The weathered debris is going to run down slope, accumulating here along the coast in a relatively flat coastal plain, and it may form sedimentary rock as it slides off into deeper water. This is going to be punched down subduction zone, where it's going to be converted into new rock, which is going to pop out of this volcano here, metamorphosing the adjacent rock, which is being uplifted as well, and maybe even uplifting the associated sedimentary rock. So ultimately, tectonics and the behavior of the sun forms our landscapes.
And that's all I have to say about that.